Okay, so Diffie-Hellman agreement was basically that you take a number and you take a power of it and you send it in public. People cannot figure out what power it is because they can't take a log. Right? That was the whole idea. This is how you exchange secret in public because people cannot take a log, and so you can send the power. And you send alpha raised to XA, and you send Q, which is mod. So you send Y, which is alpha raised to XA mod Q. So you have sent everything. If somebody could take a log, they would really figure out your XA. XA is your secret. Right? Similarly, on this side, your secret is XB, and you send basically by B, which is alpha raised to XB mod Q. Everybody has seen A and Q before, so that's not a secret anymore, and they see by B, but they can't take a log. All right? And now you both of you have a secret which is A raised to XAXB, which both of you can easily calculate, and that's your secret key. All right. And then this is supposed to have a middle attack where somebody else could just be talking to you and you never know. So this does not offer authentication, right? All right. So then Algamahl has a similar idea. It is based upon Diffie-Hellman, but he exchanges a slightly different number in the second on the response. So basically, we'll see that. In this case, instead of waiting for the key to be established and sending the message, he saves one message by sending two numbers. One of them helps you find the key, and the second one finds the message itself. So let's see what he does. He takes alpha, XA, and Q as before, and sends you A, Q, and YA. YA is simply alpha raised to XA. And here he selects another random key K, which could be called XB. He selects K, and then he selects capital K. He computes capital K, which is Y raised to capital K, which is very similar to, if you go back to the previous slide, this would be, capital K would be YB. Okay? Now instead of sending YB, he sends alpha raised to XA mod Q, C1. Directly. And then if M is your message, then he does K times M mod Q, and he sends C2. So you send C1 and C2. First one gives you the idea of first one helps you establish the secret, and the second one basically gives you the message itself. So what you do is on this side, if you have C1, you can just raise it to power XA, that gives you K, which was by B before. And then in C2, if you divide by K, you get M back. All right. While division might be easy, but people don't know K. So K is a secret. And basically that is not sent in public. What is sent in public is C1. And so you can see by calculations here that the K can be calculated. If you know XA, you can calculate very easily K. So this is another way of exchanging message in public in a secret way. Again, both of these are based upon the same idea that log is difficult. Well, a numeric example for the same thing. Suppose you have XA is equal to 5, alpha is equal to 10, and Q equal to 19. So you take alpha raised to XA, 10 raised to 5, mod 19, and you can do that in Excel or whatever, and you get number 3. So you send 10, 19, and 3. Now obviously, it is very easy to break this one because numbers are so small. If 19 was large number, obviously you won't be able to do that in Excel. And so basically that is what the whole thing is about, right? So you just send it here. Now if select random number k is equal to 6, raises y at 3 raised to 6 mod 19, get 7. Then C1 is alpha raised to k. Alpha is 10 raised to 6 mod 19 is 11. And capital K is 7 already. So the message is 17. Then we take 7 times 17 mod 19 with 5, and we send 5 on the other side, and we send 11 on the other side. First thing the other side does is calculates 11 raised to 5, the XA that he already knows, and gets 7 back. And then it divides 5 by 7. To do that, it needs 7 inverse that it can do by the tabular method. Let me taught you how to get inverse. It comes out 11, multiplies 5 by 11, and gets 17 back. Any question about this method?
So, also you can write a layer for public key, so we are known to.
See, the thing is, whatever is in between those two boxes is public. Because you are sending it on a wireless medium, let's say, and everybody can receive it.
The only thing unknown here is K.
Is what is inside the square boxes. The XA is unknown, little k is unknown, capital K is not sent on the wire, so that is unknown to public. So the left side knows XA, right side doesn't know and doesn't need to know. The right side knows K, the left side doesn't really need to know little k. It only knows capital K. Alright, now we come to a real mathematical system called elliptic curve cryptography. 7 years ago, it was not very popular. I remember when I first time taught a course here on security, we didn't do elliptic curve, but now it is part of several standards. So it has suddenly come in, and you need to know about it. So we'll take you through all the math. And so elliptic curve also provides another method of public key. Basically, the problem and the thing that we are looking in public key is to find a problem which is very hard to invert. So the RSA people realize that the log is very hard. Actually, DS realized that log is very hard. So they came up with this exponentiation method. And some people figured out that solving elliptic curve problems is very hard. And we'll show you, these are hard problems. Even for small numbers, they are hard. I spent about 3 hours last night between 12 and 3 o'clock this morning trying to work on a little problem. And finally, I did it, but not to my satisfaction. These are hard problems. We'll tell you about elliptic curves, okay? And the thing is, because they're harder than exponentiation, with a small key, you can get a lot more security. Because even with a small key, people are not able to break it. Whereas with the exponentiation stuff, we need 1024 keys today, 1024 bit keys. With this one, you might be able to do with half that or maybe 1/4 of that size. So the keys are smaller. However, the work is not smaller. Okay? So what is an elliptic curve? An elliptic curve is this curve. Y square is equal to x cubed plus ax plus b. Y square, so this is a square in y, but cubic in x. Alright? Because it is squared in y, basically it is symmetrical around y axis here. Whatever answer satisfied plus, it's also the minus side, if you take a square root, right? So this is a symmetrical curve, and so there are only two parameters, A and B. Everything else is fixed. And you can select A and B to whatever value you want, as long as it is not 4A square plus 27B, 4A cube plus 27B square equal to 0. If you select that, then it becomes a curve which is basically what we call degenerate curve. Basically, it might be just a straight line or point or something. So you won't get into that one particular combination, but other than that, all values of A and B will work. And so what we do is we define now operations on this curve. We define operations such that we can now make fields. Remember the groups, the fields, the things we talked about, rings that we talked about in one of the chapters. Those are all going to be used here. So we're going to make a field, Galois field. Basically, the way we define addition operation is as follows. If you take 2 points on this curve, P and Q, their addition is defined as the reflection of the intersection of the line going from P to Q. So let's do that one step at a time. You take P and Q, draw a straight line through them. It will intersect the graph somewhere. Then you take the reflection of that graph on the other side. That is the sum. So P and Q sum is R. Okay? If P and Q are same, then basically this line will not intersect anywhere else. It will just be a tangent, right? And then the reflection would be something different, right? So basically the way it is that so then there is a special formula for when P and Q are same. But interesting thing is, by defining plus this way, it follows all the things that we need to form an abelian group. Abelian means commutative group. Abelian means you can put A plus B equal to B plus A. So if you were to add P plus Q, the same point you will get if you do Q plus P. Is that visible? Whether you do Q plus P or P plus Q, you get the same point R. So this is commutative. And it has an identity. If you take the point at infinity and you connect P with that, the intersection will not be anywhere on the graph, but it will be right at P, and so the reflection will be right there. So basically that is 0. That's an identity, additive identity. To double a point P, you find the tangent and find the reflection, right? And closer. For every P and Q, the sum is in the set. If you define the set as the set of all the points on this graph, on this curve actually, then this is a closed group. Okay, the sum of any 2 points is in the same thing. And everything has an inverse, and is commutative. Okay, so this satisfies an abelian group. All right, but how do you find these things? You have to calculate them, and you go back to your trigonometry or whatever, and then figure out that if you want to add P and Q, and somebody gave you the x coordinate of P and x coordinate of Q, then you have to find the intersection and find the reflection. And the book has already done it for you. Basically, delta, which is the slope of this line, PQ line, is yq minus yp divided by xq minus xp. That's the slope of that line. If you want to find the sum r, then xr can be shown to be delta square minus xp minus xq, and yr will be equal to delta times xp minus xr, which xr is this r, right? Plus y minus yp. So these two formulas you can derive, and book has already given it to you. If you want to make P plus P, which is 2P, then the formula for delta becomes different, because you see, if you put yq equal to yp, it will be 0 upon 0. And so that's not a very good formula for delta when p is equal to q. So if you then you have to find the tangent, so given the graph formula, you can easily find the tangent, and its slope will be equal to 3xp square plus alpha divided by 2yp, and then you go back and put this into the same formula. You get delta square minus xp minus xq, which is 2xp, and yr is equal to same way, delta times xp minus xr minus yp. So the main thing is the delta, which is the slope of the tangent here. Alright, so now we know how to add 2 points. By adding 2 points, we can get, but at the same time we can get 2p. If you want to get 4p, what do you have to do? You have to find first 2p by using this formula, then add them, use another set of formula, the same similar formula to find the slope and all that, and then that will give you 4p, 8p. If you want to get 7p, you have to find 4p, 2p, and 1p and add them. This is as difficult as exponentiation. Remember, when we asked you to find 5 raised to 125 or something like that, basically you have to expand 125 into binary numbers and calculate all the powers and then multiply them together. Same thing. One thing I didn't put here is that everything is mod. So you have to select a number, a prime number. So all these calculations will be done with respect to that prime number. Second thing is that in our application, all these numbers are integers. So while this looks like a real number problem, and we showed you example of real numbers, in application for the cryptography, we will do everything mod and everything in integer. Okay? So anytime there is a division, for example, this division is not straightforward. If suppose you get 15 upon 7, how are you going to calculate it? You need 7 inverse. So you go back to the tabular method to find inverse of 7. So convert the division problem into a multiplication problem, multiply it, take the mod, and things like that. Okay. So there is a lot of calculation to be done to calculate just 2p. So finite elliptic curves. So basically for cryptography, this is infinite, by the way. This is infinite because the number of points on the real line is infinite, right? So this is not what they are going to use. They are going to use finite. So we'll just use integer points. So there are 2 ways to do it. One is that you select a prime number and select 2 values a and b. Those are the 2 parameters of that curve. Remember y square is equal to x cube plus ax plus b. A and b are the parameters. Over zp, z is the integer line, p is the prime number. So use integer modulo a prime, and it can be easily implemented in the software. So this is one way to do elliptic curve cryptography. Another one is to define e2 raised to m ab over a Galois field 2 raised to n. So remember those polynomials we saw? How do you do multiplication with polynomial x raised to q or something like that? We saw those. So you can do that too, and that's very easy to implement in hardware. Because when you implement in hardware, then binary curves are used, and for software, these curves are used. Okay. So addition is as difficult as multiplication, and repeated addition is like exponentiation. So it's very easy to calculate k times p. I mean, not easy, but after some calculation you can do k times p. But if I gave you k times p, you cannot calculate k. Okay, it's very hard to find k given q and p. So the problem is basically discrete log. It is harder than exponentiation. So here are a few examples. So let's take E2311. So the prime number is 23, and the parameter A is 1 and the B is 1. So the curve is y square is equal to x cube plus x plus 1, and everything will be done mark 23. And all the numbers will be positive, so you won't take the negative numbers. So now, for P plus Q, the formulas are same that we gave you before, and so better to go to the example. So we want to add 310 through 310. Now 310 is a part of the graph. Basically, if you put here 10 squared is 100, and on this side you put x cube. 3 cube is 3 times 3 times 3, 27, plus 3, 30, plus 1, 31. 31 mod 23 is how much? 8. And on this side, 100 mod 23 is 8. That's the 8, right? So this point is on the curve. 310 is on the curve, but you want to add those two numbers to calculate the slope. And somehow the book, in the middle of everything, this is something that is not a good style. They change capital delta to now lambda, so that is the same number slope. So lambda is, now you calculate the lambda by putting all those formulas, and you get lambda equal to 1/4. Now 1/4 means that now you have to find the inverse of 4 in mod 23. So you write down that table, and you do that, and you'll come up with 6. Right? Once we know lambda 6, then the rest of the easy part. XR is 6 square minus 3 minus 3. So remember the formula. Formula is right here actually. Lambda times lambda square minus xt minus x cube. So basically 3. And you get 7. And YR is 6 times lambda times xt minus XR. XR was calculated to 7. So you put that new number 7 here. And you do that and you come out with 12. So 712 is the sum of 310, 310. You cannot just do visually. I mean, if I ask you 310 plus 310 how much it is, you got to do some work there. But is it clear what work you have to do? It's a lot of work. Even in Excel, it takes, as I said, for 3 hours. You know why? Because this inversion is not easy. To find 4 inverse, I mean, like basically, if you have mod 23, you need to have inverse of all numbers from 1 to 22. Because any number may show up. Right? I was working on a problem, I think maybe it is on the next slide, mod 211. So I have to have inversion of every number from 1 to 210. And the way I programmed it, it created a 210 by 210 matrix in Excel. However, then I wanted to extend it to next problem, which was 257, and Excel doesn't allow it. It has a maximum of 256. Right? So I stopped right there. But I'm just telling you that basically this is the main problem is that inversion. Other than that, everything else is easy. And so anyway, so let's just do this one. E211 0 minus 4. Actually, I couldn't put all this because this was all done last night. I have the Excel worksheet. I will show you in a minute if I can open it. But basically, 0 minus 4. Here A is 0. So B is minus 4. And the point G, let's say, is 2, 2. And you want to calculate 121 times G. Right? 121 times G. 121 is 1111101. So we know that basically we need to take 1 and then we need to take 8, 16, 32, and 64. So all of this we can calculate by just multiplying by 2 every time. Right? This is like squaring in the previous case. So G is 2, 2. Now to just square it, we need to do all this mathematics. We need to calculate lambda. We need to calculate lambda square minus. Actually, when you calculate lambda, this inversion will come up because you will have 2yg. Right? Every time you do that, there is a new yg and new inversion. So you need to prepare the whole thing. Now, so that is, I'm going to show it to you. Here is the whole thing. Basically, this is my matrix here. You see, I have hidden the columns from O through HQ, but for every number, there is an inverse here, one upon that number here, all the way up to 210. And then it repeats actually, I mean, basically. So, I mean, I could go on more, but that is not required. So basically, I had to write programs to do this one. So this took quite a bit of time. And then, there are lots of formulas here all built in. So this is the numerator of lambda, this is the denominator of lambda, then the inverse of the denominator, and then the product, and so on and so forth. And the rest is all easy. The main part is that inversion. The reason I'm telling you all this is because there is a homework that you have to do, and you have to do. I mean, you're not going to. I programmed it in a general fashion so that I can change the numbers here for A, B, N, and even what multiplier you have, what point you have. So this is a very general program I wrote. I think it will be easier to do it in a program than in Excel. I'll tell you why it is easier in program, because this inversion is very easy to do in a program. In Excel, it is brute force. So if the inversion is the main thing that takes so much time, and then when I wanted to do it for 257, I couldn't do it. I mean, basically, there were not enough columns available in Excel. But that's where we are. Any questions about this? Even though it is all difficult, but you understand what we are doing, right? And I just want to make sure that you understand what we are doing. We are just implementing these two formulas, lambda and then r, x point, y point. Main problem in lambda is to calculate the inverse of the bottom, denominator. Everything is done mod, whatever kind you have chosen. You feel comfortable doing this? Well, you have to do it once to just make sure, right? So, I mean, all right. So now, everything that we did with exponentiation, we can do with ECC. So let's start with Diffie-Hellman. Diffie-Hellman is very similar. You select a secret NA. You select, instead of alpha, we have a G here. And then we have a curve QAB. You know what QAB stands for. Q is your modulus. AB are the parameters of the graph, of the curve. To select a curve, select the base G and select a secret NA. You send out in public G, the curve, and YA. YA is nothing but NA times G. Right? Everybody can see the product, but they cannot find NA. Okay, this is very similar, except instead of QAB, we had alpha before. No, sorry, alpha was G. QAB was, I think, just Q before. And then the other side selects NB, multiplies G with NB and founds YB and sends it out. And then the left side multiplies YB with NA, and they both get YAB equal to NA NBG. And that's the secret. Okay? So this is Diffie-Hellman with ECC. The previous one was Diffie-Hellman with exponentiation. Okay, of course you can do El-Gamal with ECC, and everything else that you did before, you can do with ECC. So basically, encryption and decryption should be kind of obvious by now. You select a curve and select a point G, and then you encode any message as a point on the curve. So let's say a message M is reflected by the point PM. Now PM, when we say PM, it is actually X value and the Y value, so everything is a pair, right? So PM is a pair of numbers. The user chooses a private key NA and then computes the public key NA times G. And the second guy, B, selects NB and selects NB times G. I think this word was not in your slide when it was printed, so make sure that you put that. But basically both sides have a public key, NA and NB. Now the encrypted value is simply kg comma p plus k pb, where k is a random number. So basically, with random number you send kg and you basically send 4 numbers now. Encrypted value is 4 numbers. You want to send only 2 points, x value and y value PM, but you are going to send a pair of points. Kg is the first point, and so it will have x value and y value, and PM plus KPB is the second point, so 4 numbers. To decrypt it from here, you just do this math and you will get back PM. Okay, an example will help. And this is the example 257 which I couldn't do, but basically this is book example is in the book, so you can see all these numbers are there. I just wanted to verify those numbers, but I couldn't. So they selected 257 0 minus 4. Okay, and PM is 112 comma 26. All right, and the number B was randomly, basically the key was selected to be 101, which is less than 257, and the G point was 2 comma 2. So the public key for B would be NB times G, which is 101 times 2 comma 2, and if you did that Excel worksheet, and if you did it, the inversion, everything else you would have done, then you would find 197 comma 167. All right. So what is involved here? 101. First thing you have to do is to expand 101 into what? A binary representation, so that you know what it is, where the bits are 1, right? So you'll find out 101 is 64 plus 32 plus whatever powers of 2, right? And then you go with G, calculate G, 2G, 4G, 8G, 16G, 32G, 64G, and then you add up proper G's, proper terms to make 101G. You understand the process? This, even though the book simply says 121 2.2, we know is 197 plus 167. I didn't know that. So, that can take 2 hours. All right. Then you select K equal to 41, just a random number. You get KG, so this is the first thing you send. 41 times 2 comma 2 is 136, 128, so that is the first number you send. And C2 is basically PM plus KPB. You do all this again. All of these multiplications are done in elliptic curve. And at the end you get 246, 174, so you send those 4 numbers to the other side. The other side can do the calculation now as by the previous formula. They can find out PM is 112, 26. That's what you started with. Subtraction is easy. Subtraction is no problem. Subtraction is not easy. Subtraction is, alright. Subtraction is one set of addition. Okay, so for example, you cannot just subtract 174 minus 84 is not 26. You really have to go through all that lambda formula. Addition of 2 points is the formula, right? Lambda square and all that. You have to calculate the slope, find out the numbers. All right. Any questions about this? Is it all very clear? I mean, you really have to do it at least once, and that's why I have the homework, and you will do that this time. read once to really appreciate how to do all this with the small numbers. With large numbers, just very, a lot more complicated. So that is the strength of ECC. The strength is that key sizes can be much smaller. And so this table shows that with symmetric key, you can get 56-bit security. With ECC, with RSA, you will need 512-bit security. 512-bit key to get the same level of security, same level of hardness. And with 112-bit, you can do with ECC. Okay? When you go to large keys, like 15,000, instead of that, you can just do with 500 bits. Okay? So, based upon this graph, you can see that basically that's why we use the symmetric key all the time. Because the keys are smaller and the computation is smaller, these are very compute intensive and the keys are larger. So even this or this, they are used only to encrypt the key. When the key has been sent to the other side, then we can just go back to our DS, DES and AES and use them. Now, we already saw that we can do random number generators using block codes with AES and DES. We saw several pictures before in some chapter that how they use EDE blocks to generate random numbers. Same thing you can do with these public key encryptors. And so we'll show you that in example here. If you want to use RSA, you can take a number, a seed, take a key, and a seed, and you get a random number out. Encryption of that number, which is random actually, comes out. Some of those bits can be output as a random number, part of a random number, and some of those bits can be fed back to the next cycle. In the next cycle, you take the same key, but this as the input, put out some and take back some. And you keep doing this, and you keep getting whole sequence of random bits. So this is actually very similar to the output feedback thing we had, except that we just take some part of it out and some part of it is fed back, and this is a standard, ANSI standard. And same thing you can do with ECC. With ECC, there is another standard, NIST standard, which says you can use elliptic curve for pseudo random number generator. And basically the way you do it is that you take any initial value and then you take a point p, multiply that. So this is that p times s. This is a single number, this is a point. So this is two numbers. And then you do this addition or multiplication in elliptic curve. Whatever comes out, you take the x coordinate of that. So there are two numbers will come out, but you take just the x coordinate. And then you feed it back to, so this is a single number. Now you take another point q, which is a dual number, and then multiply that. And then whatever comes out, you take the x coordinate of that and take the least significant 240 bits. That gives you first part of the random number sequence, and then you continue this process in the next cycle. The next cycle, use this as the multiplier to p, and then continue and use that in the next cycle, the next cycle, the next cycle. Is this picture in your handout? It's not there. I probably put it last night. It is not in the book either. If you want to put it in your handout, please put it right now. And the algorithm is very simple actually. This picture is not there in the book, but this algorithm is there. Basically, all you have to do is you do this k times some, the k is a fixed number, not a random number, and so you get these 240 bits k times. So you do I equal to 1 to k. First you calculate Si by multiplying p, and then you multiply Si to q and take the x value and take the least significant value, and that's it. So the same thing is written in algorithmic form here. Okay. So pseudo random number generation based upon ECC. That brings us to the end of this particular chapter. And 4 things that we learned in this chapter are, first of all, we learned Diffie-Hellman key exchange. So Diffie-Hellman key exchange allows you to exchange the keys in public. And original algorithm was based upon exponentiation, difficulty of taking a log. So you can send the power and you can send the base, but people don't know what the log is. And now you can apply it to other methods, right? So Elgamal extended DH, change DH slightly, and instead of sending back a key, it sends back 2 numbers, and that helps you basically decrypt the key. Then ECC can be done on GFT or GF2N, and these are examples of GFT. GF2N is very similar, except that you would have lots of polynomials to multiply and divide. And so these are examples of GFP where you use the elliptic curves to add points. And addition is as difficult as multiplication in the normal world. Public key cryptography, both RSA and ECC can also be used to generate random numbers, just like the secret key cryptography can be used to generate random numbers. Okay. Homework is, first part is Elgamal, so you can just do that and figure out how to get C1, C2s back. And second part is elliptic curve. And so, you can just do this part. So this will basically, this is very, the numbers are all very small, 11, 1, 6, and so 11 is, the key number is 11. So it won't be very difficult to do mod. And then there is a lab along with this homework. This lab actually was waiting a long time because we could not work out some of the details. So there is a program called SMB DAS. And this program was written to crash Windows XPs. Basically, if you direct it at Windows XP, they will not be able to survive. Now, Windows 7 and servers and other things can survive this. So this doesn't work with new things. But the problem is because this is a well-known malware. So basically, if you have any virus protection, they will not let you install this program on your computer. And so we had difficulty installing it. Finally, we have figured it out. So anyway, so we have installed it on one machine. And so we have provided a machine where you can attack it. And then there is a protection mechanism, Snort, that can detect it and that can tell you that, yeah, somebody attacked you. Okay? So to do this, you will have to remote desktop to XPC machine. And so since there is only one machine, you will have to reserve time in advance. The best thing is to just do it, before Sunday or something like that. It's due on Monday, so don't wait till Sunday because everybody will be doing it on Sunday. So if you do it today or tomorrow or something, it's easy to do, not very difficult. We have already uploaded everything. And the detailed instructions are here. You do have to SSH to this machine.